Hello to you good people. All right, as I promised, here is a lesson on graphing absolute value of functions. We're going to go through specific examples, but before that, we're going to do a review. So this is the review part. Parent function, we are looking at y equal to absolute value of x. And this V-shaped graph that you see, and I talked about it in the last video, which I'm going to put a link on top here in a few seconds time so that you can refer back to it. It's a V-shaped graph and it is the parent function for absolute value. And remember that this function, the absolute value function, the parent function has been taken from the y equal to x function, which is a linear function. That's a parent linear function. And here's the equation of it. Here's the equation of it. And if this line, this part right here is blue, as you continuing it down, that becomes the line y equal to x. But the moment you take the absolute value of x, that means you're not going to have any negative values for y. So this y here, -1 or -3, will not exist. And the graph flips up to the second quadrant, and then you create this V-shaped graph or the mirror image of the first quadrant graph. Now, for just to go over the points or table of values setup so that you can see it again in case I missed that in the last video, let's quickly go through it again. Now I have this table here for you to set up. The first y is the function y equal to x, and the second y is the blue graph, which is the absolute value of x. So the two different functions. And with the linear graph y equal to x, whatever you choose for x, it will be for y. So y 0, x 0. So when x equal to 0 for y equal to x, so this one is exactly that equation. So y will be 0, x is 1, y will be 1, x is 2, 2, so forth and so on. Everything will be the same. Whatever x is, y will be for y equal to x. But the moment you do the absolute value, so this part, the blue y is, this one is y equals to absolute value of x, which is the V-shaped graph that you see. And so the positive doesn't change, 0, 1, 2, and 3. But look what happens when x is negative and you take the absolute value of negative value, that becomes positive. So everything that you see here that are negative, they're all positive, repeating positive, same as the top. And that's why you end up getting these coordinates flipped up and will be in the first and second quadrant for the absolute value function. That's the review. Now let's go ahead and look at the original, the standard form of an absolute value function based on, I have to make a note here, so this is based on the linear function y equal to x, where the parent function is y equal to absolute value of x, okay? Because in later videos, at least one more video that I'm going to do on this, you can use the absolute value as an operational transformation. That means you can actually apply absolute value to any relations or functions, and it will do the exact same thing. It will change the negative value for y to positive value, and it flips it over to the second quadrant depending on where it is, right? If it is on the second quadrant, it stays, but if it doesn't, if it's in the below, that means the y value is negative, it becomes positive. Okay, now let's get on with the standard form, and I made a little note here that is similar to the quadratic functions, okay? And the standard form of quadratic function, which was called the vertex form, is given by y equal to a times x minus b all squared plus c. It used to be called p and q, but for simplicity's sake, so that you can see it the same way here, I put a, b, c, where bc is the vertex and a is the compression and expansion factor, the same what it was for quadratic functions. And of course, the domain and range we're going to talk about as well. So let's go ahead and write up what ABCs are, and then come back, and we're going to use the exact same terminology, okay? So here is all the terminologies. So We have vertex is B, B, and C. If A is positive, let's look at the positive, then we have the graph that is upside up, is a V-shaped graph upside up. If A is negative, then it will be upside down, okay? So remember, reflection over the x-axis, all right? Now, next thing, you have x equals to B is the axis of symmetry. Okay, I call it axis of sim. So as you can imagine, as you can see, same as parabolas or quadratic, the V-shaped graph that you see is a symmetric graph where the line, this is the y-axis line or x equal to 0 line, right? So this, the equation of the y-axis is x equal to 0, by the way, in case you don't know. That is the equation of the axis of symmetry for this absolute value function. Okay, so we have that. X equals to B is the axis of symmetry equation. And what else? If A, let's look at it this way. If A between 0 and 1, that means is a fraction, the graph, you have the horizontal expansion. Okay? If A is greater than 1, then you have the vertical expansion. Okay? That's what you will have on both sides. So that means what happens is that the graph opens up and widens, and I went through that in the last video graphically using Desmos. You just go back to it again. And the second case, the same thing. It just kind of narrows down, it kind of closes and shoots up faster. Okay, so those are the bases for the absolute value of functions. Now we are going to go ahead and look at the first example. We're going to graph this y equal to x minus 2, absolute value of that minus 3. But before we do that, we have to write up all the necessary information. Okay, the first one, so we want to graph this, by the way. So graph everything that we know. And we need to give all the characteristics of it. So what is the vertex? Vertex is 2, negative 3. Okay, what is A? Is A positive? Well, yes, A is 1. This 1 is in front of this absolute value sign. Okay, so A, this is your A. Now it doesn't say it is 1, but if it's nothing there, that means it's 1. Okay, so A is positive, is 1, and it is congruent in terms of the actual shape of the graph. First of all, it opens up because it's positive value. The other thing is that because it is positive 1 or 1 in terms of the value, it opens up the same way as y equal to absolute value of x. Okay, so it doesn't have any expansion or compression factor. All right, now the equation of the axis of symmetry, that's just too easy. X equals to 2. You just take the x coordinate of the vertex and set it equal to that as x equal to, and that's the vertical line, and that becomes the equation of the axis of symmetry. So that's your axis of symmetry. Excellent. What else? Oh, one more thing. Let's talk about domain and range. Let's go back up. Apologies. I forgot about domain and range. The domain and range. So domain, very easy. X belongs to all real number. As you can imagine, the graph of y equal to absolute value of x goes this way forever for all values of x and goes that way forever for all values of x. Okay? Including 0, by the way. Including 0. All right? So that's that. The range. What do you think the range is? Well, the range talks about the y values. Well, can y value be anything? Well, no. It can't be anything negative, but it can be 0. Okay, so that means we have to write it up. That says, okay, the range is y values such that y has to be greater than or equal to 0, comma, y belongs to all real number. Okay, and all the number means everything. Okay, that's the real number set. Okay, so we got the domain and range. Now let's go back. Domain, Usually for all absolute values, x belongs to all real number. Okay, by the way, there are different ways of writing this as well for the domain. You can write it in the interval form, and if you do that interval form, you can do it like this. That's no problem. You can do that way. But for simplicity's sake, for this level, you can write it like that and it's acceptable. For range, you got to write it a little bit better than that. And that is, you have to kind of understand where the graph is sitting at and then go from there. Now, the lowest value in here is -3. This is the lowest value of the function, right? So if that's the lowest value, -3, that means the graph has dropped to -3. That means that all of your y values, they have to be greater than or equal to -3, and then y belongs to all real number. Okay, now we're going to graph this and you can see it exactly what's happening. All right, so let's go ahead and now graph this. Okay, so I've got this xy coordinate here, and now I'm going to plug in the vertex, which is 2 and -3. That's your vertex right there. It does open up, we know that. And because remember I said that this is congruent to the original parent function y equal to absolute value of x, that means it has the same behavior. Now, let's quickly go back. I just want to show you something that is really useful and you can do it very quickly. Whenever you have a function that is congruent to y equal to absolute value of x, that means that the leading coefficient is 1. Do you see this right here? This value right there, this is just 1. That's your a. So whenever you have a setup like that, what you will do is you look at the graph and notice that the graph goes up by one step at a time. So here it is 1, 1, you go across again 1 unit, you go up 1 unit, you go across again 1, you go up 1. Basically, you can say that the slope is 1, even though the absolute values, they don't have a slope, but taking that absolute value as a parent function from the line y equal to x, you can actually use that to your advantage. Say, okay, the slope is 1 for a line, and that kind of a same progression applies for any other absolute value that is got the same congruency with the a for the parent function. So let's go back up. So it's going up by 1 unit, and that's all it is, a step at a time. And so is the other one, but so is the other side, but the other side is symmetric. Okay, so whatever we got in here, we just map it to the other side using the axis of symmetry. So let's go back to the equation. So we have this equation right here. So I'm going to go across 1, go up 1, that's another one, so forth, so on, and here you go. And then you can test, by the way. Okay, test the value 1, 2, 3, 4, 5. Okay, so this coordinate right here is 5, 0. Now plug the number 50 back in there. So grab this 5, plug it into x. So what you will get, you get absolute value of 5 minus 2 minus 3. What is that equal to? That's 3 minus 3. Is that equal to 0? Yes, it is. So that's exactly proving what I am just saying, that you could do that. And then to find the other part of the absolute value graph, which is the V-shaped graph, remember, you just use this axis of symmetry. And this axis of symmetry, remember, goes through the vertex. This is that axis of symmetry. I'm going to use a red dotted line. And then you just go through, you say, okay, on the other side, there's another one, that's another one, and that's another one. And this one is -1, 0. And guess what? You can do a test in here as well. I guarantee you it will work, okay? And then you go ahead and you graph the function, okay? I'm just going to do a freestyle here. It's not going to be perfectly straight, but you know what I mean. I could have used the Desmos to do that, but I didn't want to. Okay, so here it is. You get a V-shaped graph. You can use a ruler in your paper. Will make it way better, nicer than I can, because I'm not using Desmos and I can't use a ruler here. So here it is. This is the graph of this absolute value function, which the parent function is y equal to absolute value of x, and is using the, using the graph from y equal to x. This is the absolute value of a linear function, right? Now, here's a question for you. We have positive x or negative x. This is when x is greater than or equal to 0. This is x when value of x is less than 0. That means you're actually drawing two different lines, okay, the straight lines. One is the positive value of x, one is the negative value of x, and that's that is noticed that, okay, what is the piecewise equation, the two piecewise equation that represents this absolute value function? I put down the first case, so the absolute value of x minus 2 minus 3. The first case is that what if this x minus 2 is positive? If it is positive, you just leave it be, x minus 2, and then just do the math. X minus 2 minus 3, so the function will be x minus 5. This is when x minus 2 is greater than or equal to 0. Okay, as a definition of absolute value. I'm using this definition right here, okay? The next one is that what if x minus 2, the next part is what if x minus 2 is less than 0? That means inside is negative. The absolute value makes it positive. That means you have to take the negative x minus 2 minus 3. And then you have to do the math. When you do the math, you get minus x plus 2 minus 3. And of course, when you do the math on that one, you get minus x minus 1. So the two piecewise function for this absolute value, y1 is equal to x minus 5. y2 is negative x minus 1. And when you look at the graph, the right part of this graph, okay, this part right here represents the top part right there, okay, and then the left hand side graph represents the other side. So you can see that is represented by that function, which is the restriction I just give you, but the two functions are this one, the second one is the red function, and the first one is the positive function. So those are the pieces, or they call them piecewise function of that absolute value. Okay, and make sure you come back to the next video on absolute value of functions, because I'm going to do more examples of that, so then you know exactly what is happening. If you found this useful, like, subscribe, and hit the notification bell so you don't miss any future lessons as I post weekly. All right, take care.